All right, this is Circular Orbits Homework 3 Debrief, maybe a month late or so, but here it is. Given everything I tried to teach you, here are some problems to solve. And the first question that came up is, yes, that's typographical errors. When I wrote the exponents, I didn't superscript or put a caret like I should have. Number one, a starship is in a circular orbit around the planet Cygnus Lensis Prime. It has a mass of 6.52 times 10 to the 24th power kilograms. Typo. The orbital radius of the starship is 14,500 kilometers. Calculate the orbital period of the starship and express your final answer in units of minutes. Well, knowing the mass, knowing the orbital radius, asking for the period, I would select Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed over gm. And in this case, I'm solving for the period. So I could start by taking the square root of both sides. That makes it 2 pi times the square root of the radius, which is in kilometers. So multiply that by 1,000, 14,500,000 meters cubed. Make sure you cube it after you multiply it by 1,000. Divided by g, stored in my calculator memory, divided by 6.52 times 10 to the 24th power kilograms. All right, so let's see what the calculator has to say for that. 2 pi square root 14500,000 raised to the third power divided by g divided by, unless you're going to have parentheses, that you still have to have a divided by symbol here, 6.52 times 10 to the 24th power, enter. And the calculator displays 16,600 seconds. So 16,600 seconds. To express that in minutes, I would divide that by 60. And that works out to be 277 minutes. Ta-da! So there's number one. Number two, a shuttlecraft orbits Kappa Felis 4. The shuttle has a speed of 3.75 kilometers per second, and its orbital radius is 8,270 kilometers. Calculate the mass of Kappa Felis 4. For this one, I would use the equation that relates speed in a circular orbit to mass and orbital radius. So v squared equals g times the mass of the central body divided by r, the orbit radius. In this case, we want to rearrange the equation to solve for mass, multiply both sides by r, divide both sides by g, and we have mass is equal to v squared times r divided by g. Taking the care to express all the units in meters and time in seconds and so forth, this would be 3,750 meters per second squared times 8,270,000 meters divided by g. All right, well, so 3,750 squared times 8,270,000 divided by g, enter, is 1.74 times 10 to the 24th power kilograms. 1.74 times 10 to the 24th power kilograms. Number three, a satellite orbits Vorta Prime at an altitude of 510 kilometers, that should be the 3 sig figs, above the surface of the planet. Vorta Prime has a mass of 7.47 times 10 and that's supposed to be to the 21st power kilograms, and a radius of 895 kilometers. Calculate the orbital period for the satellite. Express your final answer in units of minutes. So in this situation, I have the radius of the planet, capital R. I have the altitude above the surface of the planet, h, and what I really need is the orbital radius, lowercase r, which is the sum of the radius of the planet plus the altitude above the surface of the planet. So in this situation, the orbital radius is going to be 895 kilometers plus an additional 510 kilometers, meaning the orbital radius is 1,405 kilometers, and I'll leave it to the nearest kilometer for now. Oh well. All right, so I have the mass, I have the radius, I need the period. I would select Newton's version of Kepler's third law. T squared is equal to 4 pi squared times r cubed divided by gm, making this identical to the first problem as far as equations go. So t is equal to 2 pi times the square root of, the orbit radius is 1,405,000 meters. G is stored in your calculators, 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. And the mass should have been entered as 7.47 times 10 to the 21st power kilograms. All right, so 2 pi square root of 1,405,000 cubed divided by g divided by 7.47 times 10 to the 21st power, and the period is 14,800 seconds. Converting the period to minutes by dividing by 60, I get a time period of 247 minutes. If you don't convert it when I ask you to convert it, you will lose points. Number 4, a spaceship orbits Phi Cancri 4 in a period of 5.50 hours. Phi Cancri probably 4 has a mass of 2.10 times 10, typo, raised to the 20th power kilograms, and a diameter of 558 kilometers. Calculate the altitude of the spaceship above the surface of the planet. So 2 tricks here. One is I'm giving you the diameter, and I'm asking surface of the planetoid, and I'm asking for the altitude, not the orbital radius. So good thing you do little sketches that show, okay, I know the diameter is 2 times the radius. I know that the orbit radius is equal to the planetoid radius to the surface plus the altitude above the surface. So I have the period. I need to turn it into seconds. I have the mass. And so off I go and do this. I would use Newton's version of Kepler's third law to solve for the orbital radius. And that means I'm using t squared equals 4 pi squared r cubed divided by gm. And this time I'm going to rearrange the equation to solve for the orbital radius. So r is the cube root of gmt squared divided by 4 pi squared. So r is the cube root of g, times 2.10 times 10 to the 20th power kilograms times, of course, 5.50 hours must be converted to seconds. So that's 5.50 hours times 3,600 seconds per hour, and then square that. Then divide everything by 4 pi squared. And let's see what r is. So I would do open parentheses. G times 2. Want to verify? Yes. 10 times 10 to the 20th power. So GM. Now for T, 5.50 hours times 3,600 seconds per hour. Close parentheses on that one. Square it. So GMT squared divided by 4 divided by pi squared. Close the outer parentheses, raise the whole thing to the 3 to the inverse 1 power, boop, and you get a radius of 518,000 meters, 518 kilometers. Okay, well, that's nice to know. So the radius is 518 kilometers. Now, if I subtract half the diameter from the radius, so I'm going to divide this by 1,000 to turn it into kilometers on my calculator. Then I'm going to subtract half of the diameter, 558 divided by 2, and hopefully order of operations is correct. And it says my altitude is 239 kilometers above the surface of this planetoid. Number 5. A space beacon orbits Nossi 7 at a speed of 8.54 kilometers per second at an orbital radius of 7,350 kilometers. Calculate the mass. V squared equals gm over r. Solving for mass. Mass equals v squared r over g equals 8,540 meters per second, because you're not going to goof on your units ever again or conversions, times r, which is 7,350,000 meters, divided by g, which is 6.672 times 10 to the negative 11 newtons meters squared per kilogram squared, stored in the calculator. And finally, 8,540 squared times 7,350,000 divided by alpha g, enter. And the result is 8.03 times 10 to the 24th power. Mass equals 8.03 times 10 to the 24th power, meaning it's a little bit larger than our own planet Earth, assuming that's where you're from. This concludes the debrief on circular orbits homework 3.